Hi, everyone. I'm so excited to be here today as part of this wonderful symposium, and I'm really excited to tell you about some work that I've been thinking a lot about in resolving individual differences in naturalistic stimuli. So naturalistic stimuli has become increasingly prevalent in the field over the last few years. There's this wonderful edition of Neuroimage that came out, a special edition of Neuroimage that came out just a few years ago, highlighting some of the really impressive work in this space. And in particular, naturalistic stimuli have become increasingly popular for better sampling stimulus space, evoking more synchronous activity across participants, and generating more robust relationships with behavior. But I want to point out that one of the things that's driven so much of the success of this stimulus class has been the really intense computational work that's accompanied it. So each of these different relationships with naturalistics, or different effects of naturalistic stimuli, have really been advanced through different computational methods. So for example, better sampling of stimulus space has been really strongly explored with encoding models. Generating more robust relationships with behavior has been really strongly advanced by new predictive modeling methods. And I don't think this is an accident. I think that in general, when we have been talking about naturalistic neuroimaging as a field, it's been suggested as part of a broader strategy for a more reliable neuroimaging science and more reliable inferences. But as part of that, we need to continue to think quite strongly about the computational approaches that we bring to this kind of stimuli. Because with relaxed experimental control, it becomes more difficult to resolve individual variability in both space, as in functional organization, which we've heard a lot about so far, and also time, as in functional responses. And both of these dimensions show different kinds of variability, so being very careful in the computational modeling that we do is something that I think will continue to really enable us to draw more individual-specific advances from this very powerful class of stimuli. So I'm going to talk to you today about some work that I've been thinking quite hard about for the last few years along both of these axes. First, reconciling individual variability in functional organization or functional topography, and then resolving individual variability in functional responses. So, functional organization. This is a lovely figure from Alexis Toile and colleagues, but illustrates many of the points we've heard about in the symposium so far. So here you can see three different individuals. These are contrast maps for the identical task, engaging in a math versus reading task. And you can see that there are significant individual differences, although there are general patterns. However, if we are to anatomically align these subjects and then critically take the average, we lose a lot of this very important individual variability, and so it makes it much harder to trace back to individual specific estimates. So when we think about how to recover this individual variability, there are many different ways that we could do so. We've heard about two this morning. We set about to think within the broad framework of functional alignment. There are many, many different methods which propose many different transformations. We wanted to test and see what set of transformations is best to align functional spaces across subjects. And again, this is a broad class of questions, so to constrain the problem, we only considered spaces defined by activation rather than other measures, such as connectivity, which are also very powerful and actively explored. And then our next question was, are there some contexts where alignment gives better performance? So we've heard a lot this morning about parcellations and also looking across individuals. We wanted to ask specifically, can we frame this question as a whole brain alignment versus as a task-specific region of interest? So really leveraging the kind of stimuli that we're working with, does that change, in fact, the inferences that we get for how is best to resolve individual variability? So to do this with Thomas Bazet, we set and we decided on a framework by which we would benchmark these different functional alignment methods to see how well they recovered individual variability in functional topography. And you can see just a schematized representation of the framework here. So we have some primarily naturalistic alignment data in which we learn a series of functional alignment transformations. Then we had held out unrelated decoding task data to which we apply those transformations. And critically, we can train intersubject decoders on both the decoding task data that has the functional alignment applied and the decoding task data, that does not have any functional alignment transformation applied, and we can compare differences in classification accuracy, much as Jason just showed. So just to give you a sense for the kind of data that we used here, these are 4 different dense sampling data sets, which are really very useful for looking at this combination of naturalistic and individual specific signatures. And of these, 3 have unique variable naturalistic stimuli that we can use in alignment. So in Bold 5000, it was a series of still naturalistic images. In Study Forest, it was an audio movie listening, and in Courtois Neuromod, it was an audio-visual movie. And critically, we have a range of decoding tasks which are well matched to these very complex stimuli. So we looked at 5 unique functional alignment methods, because again, our question was really what kinds of transformations are best to reconcile across this variability. For the purposes of this talk, I won't walk you through all 5 of these, but I would encourage you to check out the paper if you're interested. Instead, I'm only going to focus on 2, optimal transport and shared response modeling. And the reason that I'm going to focus on these 2 methods is that one is a high-resolution method, so optimal transport is going to do a voxel-to-voxel matching, and the other is shared response modeling, which is first going to learn a low-dimensional latent factor, which can be aligned across participants, and then reprojected back up to the full high-dimensional space. So different kinds of assumptions about where we expect similarity across participants. So here are some of the results that we found. So what you're seeing here, the structure of this plot, is that everything is normalized against no functional alignment. So if we'd only done anatomical alignment, as Jason outlined, that's the dotted line at 0%. Every dot is a different cross-validation fold, so this is a different subject, held out subject. And then the dots are colored by the particular data set that they came from with its unique decoding task. And what you can see is that on average, functional alignment is recovering about 5% of the variability over anatomical only alignment. And this differs slightly by method, but in general, these are 2 quite well-performing methods. And as a benchmark for how well this is really doing, we looked and we saw if we had just done within subject-only classification on this particular data set, how well would we have expected to do? So if we compare within subject classification versus intersubject classification, we see that within subject is about 8.59% better than intersubject classification. So really, functional alignment is recovering about half of the variability that's traditionally lost to across-subject comparisons. So we thought that this was really quite impressive. So this gives us a better sense for how these 2 methods perform at a whole brain context, where we look in parcels that tile the entire brain. But instead, we can also look at task-specific regions of interest, and there we see slightly different patterns that are quite interesting. So on the right, you have the regions of interest colored by the particular data set that they've come from. And again, the structure of the plot is exactly the same as the last figure. And what we see is that optimal transport still performs very well, but shared response model shows slightly worse performance. And the reason for this is really to do with the selection of the region of interest and the particular choice of dimensionality, both of which are very hard questions, particularly in this robust context where you have a clear distinction between your alignment and decoding task, and show that these methods really need to be nuanced and used carefully in application. So when we're thinking about differences in functional organization, how we can resolve individual variability in functional organization, as other speakers have shown, our work also suggested that functional alignment can indeed improve inter-individual comparisons. It can make it easier to resolve differences in spatial topography across individuals, but that importantly, these methods need to be used with care and they need to be used consciously. So for example, the shared response model, which assumes this latent factor representation for the similarity measure, it is sensitive to the indicated dimensionality and the particular region of interest and how well it represents the signal that you're looking to align. So using these models carefully is something that we're continuing to think about the best context for. All right. So this provides one end of the seesaw effectively. If we're thinking about variability in functional topography, the other question, of course, is that with naturalistic neuroimaging, you also don't have experimental control over the exact timing of individual functional responses in quite the same way that you would in a traditional cognitive task. And so we have been really interested in thinking about how can we resolve individual variability in this temporal context. So this is a figure from Chris Baldessano and colleagues, just to show that this is actually a really rich literature here. This is showing, when fit with a hidden Markov model, how do different regions of the brain differently segment time. So what you can see is that on the color bar at the bottom, regions that have yellow or lighter colors are more likely to show very long segmentations. That is, each event that's segmented in the data has a relatively long timescale, as you can see by the larger block diagonal structure on the plot on the upper left. Whereas regions that are darker, that show this kind of purple coloration, have a relatively short segmentation timescale, so their events kind of are much more rapid, as you can see by the relatively tight block structure on the bottom left. And what this suggests is that there is this aspect of temporal variability across the brain, but it doesn't give us great insight into how individuals differently segment within this overall context of temporal variability within naturalistic stimuli in this case. So our questions coming into this were, can neural event segmentations be learned probabilistically rather than through consensus? And this was motivated in part by more recent behavioral work, in particular from Kenneth Swallow and colleagues, that shows that indeed when we think about event segmentations within a naturalistic context, we should be thinking in a probabilistic context, a probabilistic model. And then we also wanted to learn, similar to some of the work that Ruby showed earlier, whether or not segmentations could be learned hierarchically rather than through consensus to relate segmentations across participants and constrain the kind of estimates that we learn in hopes of being better able to transfer them to new contexts. So I have some very preliminary work here, and I'm just going to walk you through it. This is basically to show a motivating simulation context. So we can imagine that we have 3 subjects, which are shown on the left in the 3 different colors. And if we were to take just an average group estimate, we might see something like what's on the right. Now, this is very useful with the caveats that there are some features of this group estimate that really don't match with any of the particular subject, original subject information. So in particular, you can see that this mean on the far left, the very first mean, is pulled up because our third subject missed a change point there entirely. And we have this induced extra state because of a slight jitter between subjects 1 and 2. So they both experienced the same temporal change, but they experienced it at a slightly different time. And so in the group estimate, it looks like there's an additional state. So what we've been working on is developing a hierarchical Bayesian change point analysis model, which enables us to look at all of these time courses simultaneously and constrain them under a group prior. And what that enables us to do is recover something like the following. So now we can see that we successfully recover indeed subjects 1 through 3, what their underlying time course would have looked like, what the means would have looked like. But critically for the group estimate, we now no longer have this extra induced state that we would have otherwise been analyzing and maybe making inferences for without fully understanding that it was just an artifact of the jitter. Critically also, because this is done in a fully Bayesian framework, we can look at transition probabilities that we learn and really investigate the learned posterior for these models. So here, I really just wanted to give you a taste of that. If you're interested, I'm very happy to talk more about this model at my poster on Wednesday and Thursday. But in general, what we're working on is extending Bayesian change point analysis to a hierarchical model, and we think that's going to provide new methods for relating individual variability and timing that hasn't yet been possible with this kind of stimuli. So stay tuned for that. But overall, what we have shown is that naturalistic stimuli is a really powerful framework for investigating individual variability in both functional organization and in responses, but that it requires really careful computational modeling to really maximize the benefits of this kind of stimuli. And that by understanding the relative similarities through these different methods, we hope we'll be able to open up future work in mapping different kinds of variability to individual level behavior and cognition. So with that, I want to thank my labs, Russ Poldrak and Scott Linderman, also the Wuxi Neuroscience Institute for funding, and everyone listed here. So thank you.